Let's solve radical equations graphically. Okay, so in the last video, I went over how to solve radical equations algebraically, and the first example we did was negative x minus the square root of x plus 7 was equal to negative 5. And what we found out was that when we solved it algebraically, we got two solutions, x equaled 2 and 9. And remember, when we plugged in 9 for x, this wasn't true, so our only solution was x equals 2. Okay, so 9 was an extraneous root. X equals 2 is our answer. How could we solve this graphically? Okay, well, what we have to think about is we can interpret the left side of the equation as a single function and the right side of the equation as a single function. Okay, so what we do is we say y is equal to the left side. Okay, so we're going to say that the left side of the equation is some function, right? It's going to look something like this. I would think it looks something like that. So it kind of flattens out as we get more negative if these are our axes right here, right? And we're saying that this function right here is going to equal negative 5. So y is also equal to negative 5. So if we drew a line at negative 5 right here, right, where they intersect, that's going to be our solution. Okay, so if we go over to Desmos right here, let's just kind of flip over. Now we're going to enter each kind of side of the equation as one function. So we're going to say y is equal to negative x, right, minus the square root of x plus 7. Okay, so like I said, it kind of starts out curved and it flattens out, blah, 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 whatever. It doesn't matter a whole lot what this function actually looks like. And now we're going to say that this red function, wherever there's a solution where they intersect, that's our solution for the equation. So see how if we zoom in right here, right, at x equals 2, there is a solution at 2 and negative 5. So when x equals 2, right, this is where we'd verify like we did in the last video, when x equals 2, y is going to equal negative 5. And that makes sense because if we plugged in 2 for x, we would in fact get negative 5 on both sides. Okay, and the reason why negative 9 wasn't a solution is because, positive 9 is because remember, that's an extraneous root. So if we kind of imagine here, x equals 9, we go straight down, that doesn't work because the y value when x is 9 is 5, and the for this function, the y value is negative 13. So that doesn't work, right? Now, let's just go back to the other equation we did. So the first one we did, right, we solved it algebraically, found one was extraneous. We didn't necessarily need to graph that because we could solve it algebraically, but that's how you would graph it. Okay, now the second one we did was we got the square root of 4 plus x, right? It was this really weird one, this hard one, plus the square root of 3x minus 2. That was equal to a constant 2. Okay, and then we figured out that the solutions, right, we didn't test if these were extraneous or not, but using the quadratic formula, we figured that the solutions were, for x is equal to 5.243 and negative 3.243. Okay, so if we were to kind of do the same method here, if we were to graph it, I'm just going to move over here to Desmos. So y is equal to the left side of our equation, right? So the left side of our equation, let's just think back here. We started with the square root, what was it? The square root, just finding it here, of 4 plus x. 4 plus x. Okay, and then to that we added the square root of 3x minus 2. And we said that that was equal to a constant 2. Or sorry, I'm not going to put equals 2 here. So that's one function, and then remember our other function is going to be the other side, so y equals 2. And notice how if we zoom in, there aren't any solutions. Okay, so it actually turns out that neither of those solutions were right. So my guess is that one of them was extraneous, and one of them didn't fit our restrictions. And the reason we have restrictions is because if we look at the inside of our radicals here, our radicands, we can't take the square root of negative numbers. Okay, we can't take the square root of negative numbers, so if we had, say for example, if we plugged in, actually let's do the negative number here. Let's plug in the negative 3.2 in for 3x. So this would be approximately the square root of, I'll go 3 times the negative 3.2, because it's about that, right, minus 2. So this will be the square root of negative 6.4 minus 2, oops, minus, not 0.2, minus 2, so this will be the square root of negative 8.4 approximately. And we can't have the square root of negative numbers. So anytime we're solving radical equations, we have to add these restrictions. And all the restrictions do is they say, okay, we're going to solve the equation normally, except we have to make sure that the inside of the radicals are either 0 or greater than 0. Because if the insides here, either of them are negative, this isn't going to be a real solution because we can't take the square root of a negative number and use real numbers. Okay, so our restrictions here, remember we set the inside equal to 0, or they have to be greater than or equal to 0. Right, so 4 plus x, that's the inside of our first term. That has to be greater than or equal to 0. Same with the 3x minus 2. Okay, so now we just solve for x here. So x has to be greater than negative 4, right? And yeah, we solve for x here. X has to be greater than or equal to 2 over 3. Okay, so notice how 2 over 3 is greater than negative 4. Okay, so we're going to ignore this one, and we're just going to generalize it and say x has to be greater than positive 2 over 3. And that is the case for this first solution we got. Okay, but notice how this negative number, it's not greater than 2 over 3. Okay, so if any of your solutions don't meet the restrictions, in this case, this solution doesn't meet the restriction, we're going to immediately ignore it. Okay, but that still doesn't answer why there's no solutions when we graph it. Well, my guess is that this was the answer we got that should work, and this right here is our extraneous answer. It's our extraneous root. Okay, so this right here, my guess is extraneous, and this part right here, it just doesn't meet our restrictions. So if we could use imaginary numbers, it probably would be a solution that's valid, but we're only using real numbers, so neither of these would work. Okay, so that's the first two examples that we did. Now let's just go over another example, okay? So let's say we had, let's say we had x minus 2. Okay, I'm thinking on the fly here. Equals the square root of 2x minus 4. Okay, so remember to solve this, we would square the radical. And when we square a square root, we just get what was on the inside. So 2x minus 4. And x minus 2 squared, right? If we expanded that, it would be x squared minus 4x, and then plus 4. Okay, and then to solve for x, right, we would have to move everything to the left. So it would be x squared minus 4x minus 2x, so minus 6x. And then it would be positive 4 plus 4, so plus 8 would equal 0. And then we factor this, so this would be x, let's see, minus 2, and then x minus 4 equals 0. So theoretically, x should be equal to 2 or 4. Okay, and if we plug this in, okay, I'll just plug in 2 first. We get 2 minus 2 squared equals the square root of 2 times 2 minus 4. So we get 0 equals 0, so the 2 works. Now let's do the 4. Okay, so 4 minus 2. 4 minus 2 should equal the square root of 2 times 4 minus 4. So 4 minus 2 is 2, and then the square root of 8 minus 4, so the square root of 4 is 2. So these solutions both seem to work. Neither of them are extraneous. Now, let's see if they check out on our restrictions. So remember, we have to set the inside of the radical equal to 0, greater than or equal to 0, so 2x minus 4. The inside of our radical has to be positive or 0. Okay, add 4 to both sides, divide by 2. Basically, x has to be greater than or equal to 2. So one of our solutions was x equals 2. That's still fine because x has to be greater than or equal to 2. And obviously 4 is more than 2, so both of these work. Now let's just check it out graphically, okay? So remember, we have to set both sides of the equation equal to some function. We'll call it y. So y, our first function, is going to equal x minus 2, right? Just a linear function. And then y is going to be equal to, and if we're right, it should be equal at x equals 2 and x equals 4. So the square root of 2x minus 4. So zoom in here, and yeah, it looks like it is. So when x equals 4 and when x equals 2, the two functions, the two sides of the equations are in fact equal. So that's how we can solve radical equations graphically, in terms of taking the algebraic expression, treating each side like it's a function itself, and graphing both of them, seeing where they intersect. So now we know how to solve them graphically and algebraically, and in my next video, I'm going to talk a lot about transforming radical functions. So, but before I told you the shape of the radical function didn't really matter when we graphed it, but in the next video, I'm going to talk about how radical functions look with no transformation. So I'll kind of give you a hint. It's kind of a sideways parabola, because if y equals x squared, or sorry, y equals the square root of x, right? This is our function right here. We can imagine it as x just equaling y squared, right? So it's like y equals x squared, except it's just rotated by 90 degrees. So that's why it's kind of a sideways parabola. So I'm going to talk about how we can shift the graph. So I'll see you there.